So some examples of these conic sections would be like this beam of flashlight. If you shine against the wall, okay, you can create all the different types of conic sections if you just change the angle of the flashlight on the wall. If you cut through a tree, the cross-sectional cut of a tree would give you these different shapes. You know, the exhaust jet of engines and rockets, because the tail comes out as a cone. Lots of planetary motion. So how planets move in the solar system are going to be governed by these quadratic relationships. Okay, so these are all the planets actually move in these parabolas, ellipses, hyperbolas. Okay, we have comets that come through the solar system that are on hyperbolic paths. Complex mirrors and satellite dishes. Satellite dishes in particular, we usually see them all the time, and they're all based on these parabolic dishes, which help focus the signals onto a point. Okay, and we'll show you some of the properties of these quadratic relations in a second. So these are the different ways we do this. So we have our cones. Our planes slice through these cones in different ways to get circle, you know, ellipse, parabola, and also the hyperbola as well. Okay, so we end up with our hyperbola as it cuts through both top and bottom of the cone. So as we just get past this parabola, so parabola is our boundary. Parabola is when we slice through, just the slice is just parallel to that edge, okay, and it just forms this non-closing ellipse essentially. So if I change the angle a little bit, eventually this line will cut through this edge and form an ellipse. It might be a really long ellipse, but the parabola essentially is a boundary between a really long ellipse and a really long hyperbola. Okay, and that's really what the difference is. The parabola is kind of the boundary. So there are some properties of these that are very useful. So parabolas, they've used these for a long time to help focus things. So in ancient Greece, they used to have parabolic mirrors that would take the sunlight, and which were essentially parallel rays, and they, in a parabola, they reflect to a certain focus. So all these different rays of light reflect to one common point, and that point gets very, very hot. Okay, so they used to be able to light fires with these parabolic mirrors because they're able to focus light. The reverse is true for headlights. Okay, so if we have a headlight, we usually have a filament here, and the light comes out in the opposite direction. Okay, so the light would be going out like this, and then it would go out in a parallel ray. So we have all this light coming from one spot going out in one direction, okay, which then gives us a nice strong beam of light from the headlight. Okay, so it's the opposite effect when we talk about a car headlight. So ellipses, they have two focuses. So the focuses are here and here. So it's almost like they have two centers of circles. And one of the properties is that if we reflect, if we take a ray through one focus, it always will reflect through the other focus. Okay, so there's lots of people who design. Some physicists I've seen designed a pool table where they have a dot here and a hole here, and they can always, doesn't matter how they point it, as long as they hit the pool cue through one of the focuses, it will always reflect into the hole. Okay, so this is one property of ellipses that we have. There are many other things like acoustical effects that you can do. So there's the oval rooms where if you stand in one spot, okay, so all the sound will come radiate out like this, okay, but all the sound ends up getting reflected back to another point in the room, okay, which would be the other focus. So you can whisper very quietly at this point. As the sound kind of goes out and disperses, it kind of, there's not much sound over here or over here, but all of it comes and focuses right back at the other focus. And you can hear very clearly what's going on at this point here. Okay, so you may have experienced this effect in certain shaped rooms where they have this focusing effect of sound. Okay, so there's another one here. It's a hyperbola. Okay, so one of the properties of hyperbola is that the two focuses, so the focus of a hyperbola is here and here. If we aim a ray at one focus, the reflection off that curve will always point towards the other focus. Okay, so we have this property of hyperbolas, and we can use this property of hyperbolas as well as properties of ellipses and parabolas to help us focus things like light in telescopes. So if we take a look at a telescope, a really powerful telescope, what it does, it has kind of a really big lens here, okay, and a really big aperture, and it collects a lot of light because it wants to see from far away, wants to be able to have a lot of resolution. So it needs, for detail, it needs lots to collect lots of light. So it has a big opening. But that big opening, what happens is it gets reflected. So the primary mirror here is a parabola, so it gets reflected towards this point here. So this would be the focus of the parabola. But as it's headed towards that, it hits a secondary mirror, it's a hyperbola. So anything pointed, if they put the focus of the hyperbola at the same point as a parabola, all the rays that end up focusing on there, because they're all pointed towards that one point, they all get reflected to the other focus. So you get all this light gets reflected here, just focusing on this point, but they all focuses back onto that point. So there's a high degree of focusing going on in these hyperbolic, parabolic mirror combinations. This is how they make really, really powerful telescopes. Okay?